Hi guys, welcome to the video on sensitivity analysis of constraints. So I expect that you have basic understanding of what is sensitivity analysis. So I'll take you to the problem. Problem says that we need to maximize an objective function which is 4x plus 2y and which is subjected to two constraints c1 and c2, 2x plus 4y less than equal to 20 and 4x plus 3y less than equal to 24. And there are two non-negativity constraints, x is greater than 0 and y is greater than 0. So just to brief out, when I say sensitivity analysis on the constraints, that means I need to find out the upper limit and the lower limit of the constants in the equation of constraints. That is, I need to find out the upper limit till which I can increase this value 20, and I need to find out the lower limit till which I can decrease this value 20. Similarly, the upper limit till I can increase the value 24 and the lower limit till which I can decrease the value 24, in which my optimal solution remains optimal. So I have represented the problem in a graph where the blue line represents constraint 1, the green line represents constraint 2, and the black line represents my objective function. A, B, C and the origin represents my feasible region. So I've already solved this problem and I've got the result that Z is optimal at point C and the optimum value is 24. So I have made this graph on a web software which is geozebra.org/graphing. I've covered how to draw the graph in my previous videos. You can check that out there. I have also solved the problem in Excel solver and I have pasted the sensitivity report over here where the solver gave me the answer that for C1 the allowable increase is 10 raised to the power 30. That is nothing but we can treat it as infinity, and the allowable decrease is 8. So my upper range will be 20 plus infinity, that can be considered as infinity, and the lower limit will be 20 minus 8, that will be 12. Similarly for constraint 2, the upper limit will be 24 plus 16, that is 40, and lower limit will be 24 minus 24, that will be 0. So I already know the answers. Now let's discuss that how to solve this problem graphically or without the solver. To solve the sensitivity analysis on the constraint coefficients, which I represent by Q1 and Q2, that is Q1 will be 20 and Q2 will be 24. The most important thing I need to know is that what are the binding constraints, or what are the constraints on which my optimal point resides. So as I can see in the image, my optimal point is at the intersection of constraint 2, that is green line, and x-axis, which can be represented by the equation y is equal to 0. So my binding constraints are constraint 2 and x-axis. So let's first find sensitivity range for constraint 2. I'll represent it as Q2. So the initial value of Q2, as we have seen in the problem, is 24. So to find the upper limit, we need to take care of 3 rules. So while I have solved many problems, I made 3 thumb rule to solve sensitivity analysis problem on constraint coefficients that actually provides results without making any mistake. So this works best for me. So for the upper limit, I need to increase the constant value of the constraint until number one, the binding constraints remains binding. So in our case, constraint 2 and x-axis remains binding. Optimal point is in the feasible region and optimal point coordinates are positive. So if we are increasing the constraint constant value or the value of q2 till my all these conditions are satisfied, then I can further increase it. But if I increase it to a limit where any of these conditions are not satisfied, that means that limit will be my upper limit. So to determine upper limit of the range for constraint 2, first compute the value of constraint 2 that would move constraint 2 upwards and the optimal solution point from old C 6, 0 to new point C, that is 10, 0. And if increase further, the optimal point will go out of the feasible region. So let's see how I reach to this statement. Let me go to GeoZebra, to our graph, and I'll start increasing the value of constraint 2 constant. So let me increase it till 30 or say 28. So my point C moves from 6, 0 to 7, 0. Let me increase it further, say till 36. So my point C moves from 6, 0 to 9, 0, and I see still my all the conditions are satisfied. My point C, my new point C, that is 9, 0, is still in the feasible region. It's on the binding constraint C2 and x-axis, and it's also positive 8, 0. So that means I can increase it further. Let me increase it till 42, or say let me increase it till 45. Okay, now my optimal point is 11, 0, but it is out of the feasible region. So my second condition is not satisfied over here. That means my upper limit should be less than 45. Let me take it till 40. When the new C point is 10, 0, then my point is on the binding constraints. It is on C2 and x-axis. It is in the feasible region. It is at the border of the feasible region, and it is also positive. So that means my upper limit for constraint 2 will be 40, and my new optimal point will be 10, 0. Now let's get back to our statement. So I have moved the constraint 2 upwards, and the optimal solution point has moved from C60 to new C10, 0. I've represented it in the image over here. Now to find the upper limit mathematically and not by the GeoZebra, we have to plug this new point C 10, 0 in constraint 2 equation, which becomes 4 into 10 plus 3 into 0, which is equal to Q2, my new value, and Q2 becomes 4 into 10, that is 40. So that is my upper limit for constraint 2. Now let's find the lower limit. So to find the lower limit, the three conditions remains the same, except that I now need to decrease the constant value of the constraint until the three conditions are met. So The lower limit of the range for constraint 2 is determined by computing the value for Q2 that would move constraint 2 downwards. That is, I reduce the value of the constraint or decrease the value of the constraint, and the solution point from old 6, 0 to new C, that is 0, 0. And if I decrease the optimal point further, it will go out of the feasible region. So let's see it on the graph. First, let me take it to the original value and now start reducing it. Let me reduce it till 10. So if I reduce till 10, my point C moves from 6, 0 to somewhere around 2.5, 0. Still, it is in the feasible region. It is on the binding constraint C2 and x-axis, and it is still positive 2.5, 0. So let's reduce this value further. So if I reduce it till 5, so now my C point becomes something around 1, 0. So when my point is 1, 0, it is still on the binding constraint, it is still in the feasible region, and it is still positive. So it is satisfying all the three conditions. Now let's decrease it more. Let's take it to lower value than 0. Let's make it -2. Or maybe a greater number, -4. So if I make it -4, then you see that the point C is still on the binding constraint C2 and x-axis. It is still in the feasible region, but now my coordinates of the optimal point becomes -1, 0. That means one of my condition is not met. So my lower limit cannot be -4. It should be greater than -4. So let's take it to 0. So if I take it to 0, my optimal point is still on the border of feasible region. It is at the intersection of the binding constraint C2 and x-axis, and it is also positive 0, 0. So that means this is my lower limit. So let's go back to our statement. So I have decreased the value of constraint 2. I have moved the line downwards, and the solution point or the optimal point has moved from old 6, 0 to new value of 0, 0. But if I further reduce the optimal point, it went out of the feasible region. I've represented it in the image over here. Now to find the lower limit mathematically, I'll plug this new optimal point into the constraint 2 equation, that is 4 into 0 plus 3 into 0, and Q2 becomes 0. Therefore, the sensitivity range for Q2 is between 0 and 40. We are done with the sensitivity range for Q2. Now let's find the sensitivity range for constraint 1 value, that is Q1. So the initial value of Q1 is 20. Again, to find the upper limit, the three conditions remains the same. Now, to determine the upper limit of the range for constraint 1, we first compute the value of Q1 that would move constraint 1 upwards. But as we saw that constraint 1 is not binding constraint, the optimal solution will stay at C 6, 0. Nothing happens to the optimal solution point. And the constraint 1 can be moved upwards infinitely, and still it will satisfy the above three conditions. So let's see what happens when we increase the value of constraint 1 constant. So let's increase it till 30. Okay, so my point C, which is the optimal point, is still on the binding constraints. It is in the feasible region and it is positive. Let me increase it to 40. Still, the three conditions are met. Let me increase it to 4000. Still, the three conditions are met. My optimal point has not moved. It is in the feasible region, the common region of both constraint 1 and constraint 2, and it is positive and it is on the binding constraints C2 and x-axis. So even if I make this value as large as 99999, still there is no change. That means I can move this value, I can increase this value to infinity, and there will be no effect on the optimal solution point, which aligns with what I stated over here, and I have represented it by the two images. So to find the upper limit, I need to plug in any of the x-intercept or y-intercept of the constraint 1 line. So if I am moving it till infinity, that means either the x-intercept is infinity comma 0 or y-intercept is 0 comma infinity. So if I plug any of it in constraint 1, it gives me q1 equal to infinity. Now let's find the lower limit for constraint 1. Again, the conditions remains the same, but the only difference is that I will decrease the constant value of the constraint. So the lower limit of the range for constraint 1 is determined by computing the value for q1 that would move constraint 1 downwards until the optimal point C 6, 0 is in the feasible region. I don't care about this being positive or this being on the binding constraint, because my constraint 1 is not binding and it won't change the position of C1. But only thing that constraint 1 controls is the feasible region. So let me take you to the graph and show you how it is proved. So I'll first take it to the original value and then decrease it. So let me start decreasing it. If I decrease it to say 15, so now still my optimal point is in the feasible region. It is on the binding constraint and it is still positive. If I reduce it till 10, okay, now my optimal point is not in the feasible region. The feasible region is this part, but the optimal point is now outside the feasible region. That means my lower limit will be greater than 10. Let me make it 12. Okay, so when I make this constant value 12, then my point is at the border of the feasible region, which is the common region of C1 and C2. It is on the binding constraint C2 and x-axis, and also it is positive, that is 6, 0. So that means the lower limit for constraint 1 will be 12. I have represented it by the graph that if I decrease further the optimal point, if I decrease the constant further, the optimal point will go out of the feasible region. So now, when my constraint 1 moves through point 6, 0, I can find the value of this constant by plugging in any of the x coordinate or the y coordinate, x-intercept or y-intercept of the constraint 1 in constraint 1 equation. So I'll use the x-intercept it is 2 into 6 plus 4 into 0. This is a typo, it should be 0. And that is equal to Q1. So my Q1 becomes equal to 12. Therefore, the sensitivity range for Q1 is 12 to infinity. If I try to verify it with what I got when I solve the problem in solver, I'll get the same answer. 20 minus 8, that is 12. So the range is 12 to infinity. 24 plus 16, that is 40. And 24 minus 24, that is 0. So the range for constraint 2 is 0 to 40. Thank you.